Hello everyone, my name is Meftah Mohammed Charaf from University of Laouid, Algeria. Welcome to our presentation. Our subject is mathematical modeling of programmable decision network to simulate the socio-economic environment. As planned, we will address the following point. Point 1, introduction. We will look at the socio-economic environment and the decision networks. Next, problems and related work. After that, the specification of the proposed network. Next, mathematical modeling of the proposed network. And we'll end with a case study and conclusion. First, introduction. What is the socio-economic environment? The socio-economic environment refers to the environment that includes all the economic and social factors that affect individual companies and government. It includes economic factors such as economic growth, inflation, employment, productivity, financial markets, and fiscal and monetary policies. Social factors include demographics, education, health, cultural values, social relationship, and family structures. The interaction of these factors leads to the formation of the general environment in which individuals and institutions live and work, which affects economic and social activity and decision-making. Next, what is the importance of decision networks? Decision networks are theoretical and technical framework used to model and analyze the decision-making process in complex environment that involves many variables and interactions. These networks help in understanding how different factors influence the decision made and how these decisions interact with each other. Decision networks include elements such as agent individual organization, links, relationship, or flow between agents, and nodes, focal point of which at which decisions are made. By modeling these elements and their interaction, decision networks can provide a comprehensive view of how decisions are made in their impact on the system. In light of the complexity of the contemporary socio-economic environment, the development of new computing methods become essential to help decision makers deal with this complexity. These computing methods can include mathematical model, computer simulation, artificial intelligence, and machine learning techniques. Using these tools, decision makers they can perform different scenario simulations. Simulation enables the impact of potential decisions to be tested in virtual environment before implementing them in reality for reducing risks. They can adapting to dynamic changes. Computation tools help in adapting to rapid changes in the socio-economic environment by providing continuous updates and advanced analysis. They can improving efficiency and effectiveness. It contributes to improving decision-making process by providing recommendation supported by data and reducing reliance in intuition or personal experience only. Next, problems. This work aims to contribute to this field by proposing a mathematical model for a new programmable decision network designed to simulate the social economic environment. It addresses several key questions. The first, how can the social economic environment be modeled using programmable decision network? What are the mathematical foundation of this modeling? Next, what are the primary issues related to the network's characteristics such as loops and timing problems? And finally, what are the implementation methods for this network? Now, the related works, typology of decisions. Simon adopted an analysis to show how managers make decisions. In this regard, he proposed a typology of decisions. First, programmable decisions, repetitive and quantitative decisions where the problem is well defined and information is available. Next, semi-programmable decisions, presence of many parameters, partially reliable and difficult to obtain information, necessitating decision support tools. Third, no programmer decisions, high degree of uncertainty, numerous or insufficient information, relying on the intuition and experience of leaders. One of the most famous decision networks, a Bayesian network, also known as Bayes network, BayesNet, belief network, or decision networks, are a type of probabilistic graphical model representing a set of variables and their conditional dependencies via direct acyclic graph. There are also dynamic Bayesian networks, augmentation of the standard Bayesian network that embed the concept of time. Dynamic Bayesian networks can be used when we need to model a time series. They are able to model complex multivariate time series because we can model relationships between many time series in the same model and also different regimes of behavior. Since time series often behave differently in different contexts. As related work, also there are micro-decision process is a mathematical process for making a sequence of decisions in stochastic environment to maximize reward, to model probabilistic relationships among variables and value the likelihood of different outcomes, give framework to reason under uncertainty. Also, decision tree. Decision tree works are parametric supervised learning method used for classification and regression. The goal is to create a model that predicts the value of target variable by learning sample decision rules inferred from the data features. A tree can be seen as piecewise constant approximation. As related works, there are also influence diagrams. Influence diagrams are a visualization method that shows the relationship between the main elements of decision setting to model and analyze decision problems to show the relationship among decisions, uncertainties, and objectives to enable the understanding of the structure of complex decision problems. Now we start the specification of the proposed network. Socio-economic environment as network. The concept of the socio-economic environment as shown in figure 3 can be understood as a complex network of components interacting in an environment that can be modeled as a system of nodes and links. In this network, the nodes represent the various components such as organization, institution, or economic entities, while the links represent the interactions or relationships between these nodes. Each node and link is associated with a specific time frame, highlighting the dynamic nature of this environment. Accordingly, the proposed network models the socio-economic environment with three elements: components and relationships and environments. Now we show the mathematical modeling of the proposed network. To model the proposed network mathematically, we can use a set of mathematical functions and time-based equations to represent the nodes and links. Mathematical representation of the node. Social economic components or the environment as node. Each node Ni can be represented as mathematical functions dependent on time and its inputs. Let's assume the inputs to node Ni are I.e. of t, and its outputs are O(i) of t. The node can be represented as O(e) of t2 equals f of I.e. of t1 with d, where O(i) of t2 equals output of node Ni at time t2. I.e. of t1 is the input to node Ni at time t1. I.e. is a composite input from a set of partial elemental inputs that may have come at different times. The function is executed when the necessary inputs are available. F mathematical functions representing the internal operations of node and I, and the effect of time in this node. D. The duration of node refers to the time interval between when it receives its inputs and when it generates its output. The mathematical representation of the link social-economic relationships. The links between nodes can be represented as time-based functions that describe the duration it takes for the output from one node to become inputs to another node. If there is a link between node Ni and node Ng, the link Lig can be represented as Lig means Ig of T2 equal O I of T1 after Tig, where OE of T1 after Tig is the output from node Ni at time T1. Ig of T2 is the input to node Ng at time T2. Tig is the time taken to transfer the outputs from node Ni to node Ng. As example of our network, suppose we have a sample network with three nodes, N1, N2, and N3, respectively represented mathematically by three functions, F1, F2, and F3, and an environment E represented mathematically by the functions E, affects and affected by the three nodes, N1, N2, and N3, with links between each pair of nodes. Using this representation, entire network, as shown in Figure 7, can be described by a matrix of time-dependent functions that link each node to other. The system can be represented as below, from the equation 3 to equation 6. And the links between nodes, in case of closed loop in the system, can be represented by the equations from 7 to 12. For the execution of the proposed network, the user can select between two types of execution directions. The first, forward direction. The user selects a node or group of nodes and the program will execute them. After that, the user will change the configurations of these nodes and run the simulation again. The program then will generate a report of the affected nodes by those changes. The second, backward directions. The user selects node or group of nodes and calculates their outputs while executing dependencies of that node if there are any. Now we show the proposed network as a programmable decision network. Suppose we have a sample network with 5 nodes. Each node contains a program. 5 nodes without environment effects, with links between pair of nodes. The system can be represented as programmable decision network as below. There are 3 nodes. The first, node base price, node quantity, and node discount. Each node contains a program. Here we have two programs of 2 nodes, node tax and node final price. And so, to implement the mathematical and computational concepts explained in this work, we have developed an application based on the proposed concepts of the programmable decision network. We show in Figure 9 graphic editor of the network in the application. In Figure 10, the code editor of program of each node of the network in the application. After executing the simulation 2 times, we will get the execution report. where we can compare different outputs by different inputs, which can help the user pick the right decision. Finally, and as conclusion of this work, the aim of this paper is to propose a mathematical modeling to design a programmable decision network that will serve as conceptual background that allow developing a system to simulate the social and economic environment. The proposed programmable decision network is distinguished not being limited to probabilities and statistical concepts only in computing nodes, but rather utilizing all the programming capability of different and diverse programming language, as each node is characterized by its own internal programming independence and in terms of the design, implementation, and analysis presented in our work. It is clear that programmable decision network offer a powerful framework for enhancing and improving decision-making process in dynamic environments with potential application in various fields. It is clear that this work has promising prospects for research and development, especially in big data environment, and how to improve performance in each using appropriate algorithms. Thank you very much.